Hey everyone, we have two particular goals in mind for this section. The first of which is to take a very math-centered approach to understanding relationships that exist among sides and angles in right triangles. And then second of all, we'll look at a variety of applications in which we can further extend and use those relationships that we see in right triangles. So to begin with right here, let's just recap and talk about some of the important things that we should know already about relationships in right triangles, so that will inform us in terms of how we can go about solving in just a little while here. So within any sort of a right triangle, we know that by definition a right triangle has to have a right angle contained inside of it, right? So one of the most basic relationships that we know that exists in any right triangle is that if you label the legs as A and B and the hypotenuse as C, that the square of the hypotenuse's length is equal to the sum of the squares of the lengths of the legs, right? So that's what we know as the Pythagorean theorem. And then, of course, we also know that if we call each of these angles angle A and angle B and angle C, that the sum of the measures of all the angles, of course, are going to add up to 180 degrees. And that's not just unique to a right triangle, of course. That's true for any triangle, that the sum of its interior angles is 180 degrees, right? Great. So when we're looking at trigonometric relationships within right triangles, we know that we have these three main trigonometric functions. Now, in order to use these trigonometric functions in a right triangle, we'll usually want to input one of the acute angles in your triangle. So if I were to label, let's say, this angle right there as theta, then we would label the leg that's across from it as the opposite side, and then the hypotenuse is always across from the 90-degree angle, and the leg that is right next to the angle that we reference, we label as the adjacent side. So when we reference that particular angle, theta, that acute angle, sine is always the length of the opposite divided by the hypotenuse, and then cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And so that's what we know as SOHCAHTOA, of course. And so we can take all of those trigonometric relationships there and form what we call the reciprocal trig functions. So when we flip over sine and we get its reciprocal, it's hypotenuse over opposite, which we call the cosecant ratio. And then the secant ratio is the reciprocal of cosine, which is hypotenuse over adjacent. And then the tangent's reciprocal is cotangent, which is adjacent over opposite. And we get those reciprocal trig functions to those original three trig functions right there. So what's really important to understand about those relationships is whenever we're dealing with reciprocal trig functions or the original, all six of those, you're always taking one of them. So for example, sine, and what you put as an input into that relationship is always some sort of an angle measure. And then what you get out of that as an output is always going to be a ratio of two of the side lengths in that right triangle. Okay, so it does turn out that there is what we call the inverse trig functions. And those inverse trig functions are known as sine inverse, cosine inverse, tangent inverse, cosecant inverse, secant inverse, and cotangent inverse. Now, we also do have other names for these as well. So they can also be called arcsine, or arccosine, or arctangent, and arccosecant, arcsecant, and arccotangent are similar names that we could also call these. Now, when we're using any of these six inverse trig functions, it's just the inverse of what the six original trig functions do, which is instead of inputting an angle, you're actually going to input the side ratio, and then as an output, you always get an angle measure when you're using these inverse trig functions. So given a particular ratio between opposite and hypotenuse, we always know what that particular acute angle would be, etc. All right, so with that all in mind then, we can dig into some solving and that sort of thing here. So jumping to here, you can see that we're solving to find each indicated measure in each triangle. So if we look at that very first example there, we're solving for x, which happens to be a side length of that triangle. Now, We could possibly use the Pythagorean theorem, but we also don't know the side length of that hypotenuse, and so we actually have two unknown side lengths, so that's not quite enough information to be able to use the Pythagorean theorem. But with one known side length and then knowing one of the acute angles, we can use some trig relationships to be able to solve for x then. And so across from where that 32-degree angle is, then we would have x be the opposite side, which is what we're trying to solve for. And then the 13 that is known is the adjacent leg. So if we can relate the opposite and adjacent, we would have to use the tangent ratio then. You could also use cotangent ratio, but we'll just go for, if we can, sine, cosine, or tangent, one of the main three. So the tangent ratio, by plugging in 32 degrees then, would be equal to the opposite on top of the ratio, because opposite over adjacent, and then over 13. And so that's a true relationship. And then we can solve that for x if we do the same thing to both sides and get the x alone. And in this case, we would want to multiply by 13 to get the x alone, and then multiply by 13 here as well. And so 13 times the tangent of 32 degrees is equal to x. Of course, make sure that your calculator is in degree mode when you're entering this into your calculator. Once we solve for x right there, we do get a value of about 6.25 for the length of x right there. Great. All right, so we'll jump to the next example here where we're solving for x, it looks like again. This time x looks to be on a hypotenuse, and we're also relating it to a 10.8 that if I reference the 57-degree angle would be the opposite side. So we would be able to use a sine ratio, since sine is opposite over hypotenuse, and be able to sine the 57 degrees angle. And then that would be equal to the opposite on top of 10.8 divided by the hypotenuse of x. So it's a little bit different than the first example because now x is on the bottom of this fraction. So one thing that we could do is we could multiply by x to undo the dividing by x, and then multiply by x over to this side as well. So now we get that x multiplies with the sine of 57 degrees, and that equals the number 10.8. And then you can get the x alone because you could divide by the sine of 57 degrees to cancel that out, and then divide this by the sine of 57 degrees, and then x would be equal to what that fraction is right there, 10.8 divided by the sine of 57 degrees. And so we would get x to be approximately then 12.88 units of length once you enter that into a calculator then. And then the last example up there is actually asking us to find what the measure of theta is up there. So we need to find that angle measure, and we don't have this other angle measure either, so we wouldn't be able to use the fact that the angles add up to 180 degrees. What we could do, though, is we could relate together the side that is adjacent to theta, which is 4.4, and then this 11, which happens to be the hypotenuse across from the 90-degree angle. And adjacent and hypotenuse could be related through the cosine ratio. So we know that cosine of whatever that angle is would be the adjacent of 4.4 over the hypotenuse of 11. But then to get theta out of that, we'd have to do an inverse cosine. So doing inverse cosine of the ratio of 4.4 over 11 then will give you what that acute angle comes out to be. And in a calculator, that's going to evaluate to come out to be about 66.42, and that would be in degrees then. So we jump to example 2 now. The instructions that we're having here is that we're asked to solve the triangle. What that means is we want to find all of the side lengths and all of the angle measures of the triangle. We're asked to solve the triangle. So we actually do have some of the information already. So of the angle measures of A, B, and C right here, we do have the 90-degree angle, which is angle C. And then we also do have the acute angle A's measure, which is 53.13, but we don't have angle B, so it'd be pretty easy to find angle B because we know that the sum of all three angles in a triangle adds up to 180. So if we subtract 90 and we subtract 53.13 from 180, that forces this other angle here to be 36.87 degrees in measure. Then we also have to find all of the side lengths. So when we label sides of triangles, you'll see that this side right here is called lowercase c because across from it it's called capital C for its angle. So that means that this side right here would be lowercase b because it's across from capital B, and this side right here would be lowercase a. So let's maybe try to solve for a first of all, since we don't have that measure. And since we don't also have b, we can't use the Pythagorean theorem right away. So we're going to have to do a little bit of trig. So if I were to reference that 53.13 degree angle, this here would be the opposite side. And then I could relate it with a side that is 10 long, which is the hypotenuse. And if I use opposite and hypotenuse, I could use a sine ratio. So the sine of 53.13 degrees would be the opposite side length of A all over 10. And then to solve for A alone, you just need to multiply both sides by 10. So 10 times the sine of 53.13 degrees then would be equal to the length of A. And then A is, in my calculator, it's like 7.9999, which is basically 8, right? And so that's going to end up being the length then for A. Side A is 8 long. We also know that C is 10 long, as was given. And then we just need to find B. So we could use trig, but since we actually now have two of the side lengths and it's a right triangle, we could just use the Pythagorean theorem from here. So the 10 squared would be alone, because that's the hypotenuse. And that would equal A squared plus B squared. So 100 would equal 64 plus b squared, and if you subtract 64, you get 36 equals b squared, and then you take the square root, and then 6 ends up having to be b. So that would be 6. And then those measures right there are the 6 measures we needed to be able to solve this triangle. And then one more example of being able to solve a triangle here. What's a little bit different in this triangle is instead of being given 2 of the angle measures like last problem, here we're actually given 2 of the side lengths. So we know that side B is 8 long, and we also know that side A is 15 long, but we don't know what side C is. And side C happens to be the hypotenuse, so we could use the Pythagorean theorem to find that. So 8 squared plus 15 squared would be together on the same side, and the hypotenuse squared would be on the other side. This gives you 64 plus 225, and you adding those together gives you 289. Is c squared, and then you can square root, and you get the nice whole number 17 for, not c squared, for c, for that last side length right there. Great, and then we just need to find the 3 angle measures, and we'll have the triangle solved. So we want measure of angle A, and then we want measure of angle B, and we also want measure of angle C. We have measure of angle C given to us, which is 90 degrees. So we just need to find measure of angle A or measure of angle B. So how about if we go for measure of angle A? If I'm going to go for measure of angle A, then let's reference it and then use some trig to be able to find the angle. So perhaps we'll use this side across from it, which is the opposite. And then if we also use the 8 that was originally given, that would be the adjacent side. And then we could use a tangent ratio, knowing that we're using opposite and adjacent. So tangent of that angle A that we referenced would be the opposite of 15 divided by 8. And then that could be put into an inverse tangent, that ratio can, to give you what that angle theta is going to be. So when you inverse tangent the 15 divided by 8, then you get that theta is about 61.93 degrees. And so that was angle A, and so this here is 61.93 degrees. And then we can also solve for the measure of angle B, because we can subtract them all from 180. So 180 minus 90 minus 61.93 leaves this last angle here to be about 28.07 degrees. And we're done. So now that we've looked at those just mathy number only types of problems with right triangles, we're going to look at a variety of applications in which we can apply various relationships in right triangle trigonometry here. So to begin, we've got this first scenario where a photographer's camera has a picture angle of 52 degrees. And the picture angle, of course, limits the width of the photo that can be taken, right? You can't just like take a 360 panorama shot without like spinning yourself around, right? So we can only capture an angle of 52 degrees. The photographer is wanting to capture a picture of a line of 12 students that's 26 feet long. And we want to know how far that photographer must be from the line of students in order to center all 12 students in the picture, right? So you basically, right, have a camera, and that camera is only able to capture an angle of 52 degrees, right? It can only go out that far. Now, out here somewhere is this line of 12 students that's 26 feet long that you want to capture in the image, right? So we want to try to figure out how far away this camera person needs to stand away from the students, right? So this right here would be that distance that that camera person needs to stand away. And we want to solve to find what that distance is. Now, the nice thing about that distance is it's a straight shot distance to that blue line, which means that we're getting a 90-degree angle that's being formed right there with the line of students and then the distance away from the camera, which then forms a couple of right triangles for us. So if I draw out separately one of those right triangles right here, then we would know that we're trying to solve for that distance d right there between the camera and the center of the line. But then also this right here has to be 13 feet because it's going to be half of the length of that line of students. And then also that 52-degree angle gets cut perfectly in half, which means that this is going to be a 26-degree angle right here. And then this is actually sufficient enough information to solve uniquely for what the distance d would be using a little bit of trig. Because if you reference this angle here as theta, this here would be your opposite side, and then the distance d is your adjacent side. So we could use a tangent ratio, since that uses opposite and adjacent, and tangent of 26 degrees then would be the opposite of 13 feet divided by the distance d. So if you do a little bit of solving where you multiply by d to both sides, and then you'd have to divide by tangent of 26 degrees, d solved for along would end up being 13 divided by tangent of 26 degrees. If that's confusing for you, then go through the algebraic steps of that. We saw a very simple example of the solving of this earlier. And then you just enter that into your calculator. That should tell you what d should end up being. So the distance that the photographer would need to stand away from the center would have to be about 26.65 feet away from that line of students. So for some problems that we'll be looking at just a little bit, there will be some terminology of angles of elevation and angles of depression that we want to familiarize ourselves with here. So when we're talking about an angle of elevation is an angle that goes upward, but what's really important about that is it has to be an angle that comes from horizontal. So a great example of that is this: you have like a person, right? So normally with their eyes, if they're looking, they would be looking in this direction, which of course is horizontal, right? But if they have to raise their eyesight to look upwards towards the sky somewhere or whatever they're looking at, right? Then they would raise their eyes up in this direction and then elevate their eyes up to some object that's up in the sky, right? So maybe there's like a bird or whatever up there in the sky, right? So this angle right here, this angle measure is called an angle of elevation. So it's always an angle that's risen from horizontal, okay? Now that bird, if it was also looking horizontal, would need to look in a downwards direction, so pivot their eyesight in this direction to be able to look down at whatever's below, whether it's a person or a rodent that's hunting or whatever it might be, right? So an angle that goes downward from horizontal is what we call an angle of depression, okay? So just to drive this home a little bit here, let's suppose that you've got a couple of, taller buildings, but one of them is a little bit taller than the other. And if you've got a person standing on top of the taller building and then a person standing on top of the other building here, right? So if like this person that's on top of the building, the higher building, is looking down towards the other person, right? You might be able to see like, oh, we could like make a right triangle out of this, right? And then you can think, okay, well then is this angle right there the angle of depression because that's the angle going down? And it turns out that that angle where I put the theta is not an angle of depression. Because by definition, an angle of depression and an angle of elevation has to pivot from horizontal, either upwards or downwards. And what we see right here is that this right here is vertical, and that's not what we want to be pivoting from to get an angle of depression or elevation. So to get an actual accurate angle of depression from that person that's at the top, you have to start from horizontal. So what that means then is you have to start your angle from horizontal, so like the person who's looking straight forward, and then pivot that downwards like this. And so it's this angle theta right here. That would be your angle of depression. And you're still able to make a right triangle out of this because then you can just make a straight shot down like that, and then you can see you easily get a nice right triangle out of that. So just understand that you always get angles of elevation and depression when you pivot upwards or downwards from horizontal. All right, so here's a nice example that does utilize the terminology of angles of depression or elevation here. So in this problem, we know that the traditionally accepted minimum pitch of a roof that has asphalt shingles is a 2:12 ratio. So we're talking about roofs of buildings and roofs that happen to have asphalt shingles, right? So this term, the pitch of a roof, is really just a synonym for the word slope. And so we want the minimum pitch to be a 2:12 ratio. And if you think about what slope means in the context of linear equations and such, right? It's the ratio of the amount of rise to run in some sort of a slanted surface. So that means that this 2 right here corresponds to the amount of rise, and this 12 right here corresponds to the amount of run. So basically that means for every 12 units of run, there's 2 units of rise in some sort of a slanted surface, right? So this red slanted portion would have to be kind of like the minimum pitch of your roof, meaning that if that's the minimum, the pitch has to be higher, so steeper, because you want your snow and rain to fall off the roof, because otherwise if it builds up on your roof is going to collapse from all that heavy weight on it, right? Okay, so for a house that has a roof with an isosceles triangle cross-section that's 42 feet wide, we want to know what the angle of elevation is for the roof, and then also what is the length of one of the sides of the rafters, right? So, yeah, we basically just have a isosceles triangle cross-section for your roof, right? So this would be an isosceles triangle where 2 sides are the same, of course, and like here's your house, right? Okay, so what we want to try to find here is we want to try to find the angle of elevation of the roof, which means that from horizontal here, we want to pivot upwards and talk about what is that angle of elevation of this roof, right? So we do know that the isosceles triangle has a cross-section that's 42 feet wide. So all the way across, like this house is 42 feet wide for its cross-section, right? Now, I think we're going to need to cut this roof in half, because when we cut this roof in half, we can form this yellow triangle right here, which is a right triangle, of course, right? And so with that right triangle, then we get a bottom side length there that's going to have to be half of the 42 feet cross section. So it's going to be 21 feet long right there, and then have a 90-degree angle that you're seeing right here. And then we're trying to solve for this angle right here, right? This angle of elevation. Now, if we want to find that angle, we need to know one other side length of this triangle. And that's where this rise over run is going to come into play for us right here. Because we know that for every 12 units of run that we have right here, we should have 2 units of rise right here. And so since this is a known 21, we should be able to solve for what that x is, knowing that they're proportional to this 12:2 relationship, right? So for 21 units of run, we should have x units of rise, which then is equivalent to having 12 units of run for 2 units of rise. So that's like a proportion that you can really solve then. So 21 times 2 is 42, and 12 times x is 12x. Set them equal to each other and then divide by 12. That tells you that x has to be 3.5 then. And so this here is 3.5. And we know that that right there is a 3.5 height from the middle of the roof, right? So now we should be able to solve in this triangle for theta given 2 of the sides. So you'll recognize that across from theta, the 3.5 is the opposite side, and then the 21 is the adjacent side. So opposite and adjacent could be utilized in a tangent ratio. So tangent of that acute angle measure would be the opposite of 3.5 over the adjacent of 21 then. And then just use the inverse tangent by putting that ratio inside of that, and that should tell you what the angle of elevation is going to be. So inverse tangent of that is about a 9.46 degree angle. Not too crazily steep right there, 9.46, but enough to make some stuff fall off your roof, right? And obviously the steeper it is, probably the better it is for the snow and rain stuff to fall. All right. Jumping to example 6 right here. In Telluride, in Colorado, there is a gondola ride that provides a spectacular view of the town of Telluride and also other surrounding mountains. The gondolas that begin in the town of Telluride, they begin at an elevation of 8,725 feet, and they travel a distance of 5,750 feet up to Station Street Sophia, whatever that is, SSS, right? Whose altitude is 10,550 feet. The gondolas then continue 3,913 feet downwards towards Mountain Village because it's a little bit of a lower elevation than where SSS was at 9,500 feet of elevation. So we do have two different questions that we are asked to find here. We're asked to find number one, what's the angle of elevation from the town to SSS, and then also what's the angle of depression on the gondola ride down from SSS down to Mountain Village, right? Okay, so let's kind of sketch out what we have going on right here. So we have the town of Telluride, and from the town of Telluride, there is a gondola that goes upwards to SSS. Now, it does tell us that you travel 5,750 feet to get up to there. And there is a significant elevation change that happens there because you start at an elevation down here of 8,725 feet, and then you rise up to an elevation of 10,550 feet to get there, right? And then you travel downwards a distance of 3,913 feet to get down to Mountain Village, and Mountain Village ends up being at an elevation of 9,500 feet above sea level. All right, so with this then, we want to find an angle of elevation from the town to SSS first, and then the angle of depression from SSS down to Mountain Village. So let's start with the first part, which is just the angle of elevation. So what we'd want to do is we want to compare from horizontal, what is the amount of angle change to rise, right? So right there, that would be what that angle of elevation is going to be. So we do know that the diagonal distance of the gondola is 5,950 feet, but then we also do know the elevation change. So if we change in elevation from 10,550 and 8,725, that means there was a straight up and down change of 1825 elevation right there. So that does give you two side lengths in this right triangle right there, which would allow you to solve for theta. So you'll recognize that this here was the opposite side and this is the hypotenuse. So you'd be able to use a sine ratio. So the sine of theta would be equal to the opposite of 1825 divided by the hypotenuse of 5750. And then you can use the inverse sine ratio to find what that particular angle is going to be. So then we get that theta is about 18.5 degrees in elevation there. Okay. All right, and then if we go to the angle of depression from SSS to Mountain Village, we'll have to kind of make a smaller triangle here because we don't go down all the way to the level of elevation that Telluride is at. We only go down to 9,500 feet of elevation. So from a change of 10,550 to 9,500, that is a 1,050 feet change in elevation. And then we also know that diagonal distance. So we should be able to find the angle of depression here. Now we do have to be maybe a little bit careful because technically an angle of depression actually needs to go from horizontal and then pivot downward. So in all technicality, we should be probably looking at this green triangle then. But the distances are really still going to be the same because this diagonal is still 3913. And then this vertical change is still 1,050, and here's your theta, and you're still trying to find what this angle of depression is right here. So we're using this opposite side length here, and we're using this hypotenuse side length right here, which means we should use a sine ratio. And the sine of this particular theta now would be the opposite over the hypotenuse, like you're seeing right there. And then we can use a inverse sine to find what that theta angle measure is. And we get that theta is about 15.57 degrees in measure there. And then in example 7 here, we have that the sun is casting a 31-foot shadow on a tree. And then a person uses a clinometer to measure a 70-degree angle from the tip of the tree shadow to the top of the tree. and we want to determine what the approximate height for that tree would be, right? So you do have a tree, right? And then you've got the sun up here in the sky. It's casting a shadow down upon it, right? So that sunlight comes down upon the tree, and then we get this shadow. And the shadow that we have right here says, or we know that it's a 31-foot long shadow, right? So a person uses a clinometer. And what a clinometer is just an angle measuring tool. And they measure a 70-degree angle, and that comes from the tip of the tree shadow up to the top of the tree. So here from the tip of the shadow up to the top of the tree, then we see that we get a 70-degree angle, right? And since the tree is standing upright, we do have a nice 90-degree angle down here at the base of the tree. Nice little right triangle that we can work with. We want to know the height of the tree. The height of the tree would be what this distance is here, right here for h, which happens to be the opposite side from the 70-degree angle. And then we do know the 31 is the adjacent. So if we have the opposite side and adjacent side, we can use a tangent ratio. So tangent of the 70-degree angle would be equal to the height of the tree divided by 31 feet for the adjacent length. And then, of course, equivalently, 31 times the tangent of 70 degrees would be equal to the height of the tree. And then evaluating that in a calculator, we come up with a height to be about 85.17 feet. That there. To help us in example 8 just a little bit here, we do want to understand some things about compass bearings. So you should be familiar with these directions of north, east, south, and west, of course. If we had a compass bearing that said something like this, like north 60 degrees east, what that means is that from north, you need to pivot towards the east an amount of 60 degrees. So this red arrow right here shows us that we would be traveling north. But if we pivot towards the east, you'd pivot in this direction, and you'd want to pivot in the amount of 60 degrees. So a 60-degree angle would kind of look approximately something like this, where here you'd have a 60-degree angle. So it's now this red arrow direction that you see, which would be a direction of north 60-degree east, right? If you had like north 2 degrees west, you would again start from north, but you pivot towards the west and just an amount of 2 degrees. So something like this right here would be just 2 degrees nudged towards the west from north, right? And then we also oftentimes will have directions that will kind of start with the south. So if you had south, say like 20 degrees west, you'd pivot 20 degrees from south in a westerly direction. Or if you had, you know, like a south 45 degrees east, then this right here would be about south 45 degrees east, pivoting 45 degrees from south towards the east, right? All right, so with that then, we can apply that in this particular problem then. So in this problem, we have that a forest ranger is sighting a fire directly to the south. A second ranger is 7.5 miles directly east of the first ranger and sights the same fire at a bearing of south 26 degrees, 23 minutes west. We want to know how far from, this is supposed to be Forest Ranger A is the fire. So just think of this as being Forest Ranger A, and then this second ranger as being Forest Ranger B. Okay? All right, so we do have that Forest Ranger A sights a fire that's directly to the south. So in this direction right here, we've got this fire. So everything is all up in flames down here, right? All right, and then second ranger is 7.5 miles directly east of the first ranger. So east is this direction, and it's exactly a distance of 7.5 miles this way, where we find this second ranger. Now, the second ranger sights the same fire, and we know the bearing at which they sight this same fire. So the bearing that they have is, first of all, south. So we'd have to go, first of all, in a south direction, but then pivot this amount of angle measure in the direction of west. So 27 degrees would only be kind of pivoting about this far, right? And then that would be into the direction of the fire. And this is 27 degrees and 23 minutes pivoted towards the west from south, right? So we want to try to figure out how far away A is from the fire. So we want to try to figure out this distance X right here, how far that first ranger is from the fire. So it'd probably be advantageous for us then to use this triangle that we have right here, because we know that this angle right here would be a 90-degree angle, because that's the amount of angle measure we have between south and east, of course, right? Um, so it'd be helpful to realize that this angle measure helps us to determine this other angle measure because they're going to be complementary. So if you were to subtract 90 degrees and 27 degrees in 23 minutes, we would first of all know that we would get 37 minutes because the 23 minutes and 37 minutes have to add up to 60 minutes total. And then when you do 90 minus 27, you get 63 degrees, but it really needs to be rounded down to 62 degrees because these two things right here that I just shoot arrows to add up to 1 degree. So that's why we have to account for that 1 degree difference. So that would be what the angle measure is that we have in this acute angle right here, 62 degrees and 37 minutes. And so now if we were to reference this angle, we would have that this here is the opposite side and this here is the adjacent side. And so we could use a tangent ratio where the tangent, all of that angle measure would be the opposite of x over 7.5. And we want to input what that measure of 62 degrees, 37 minutes is into the tangent. But of course, you'd want that in just normal degree measure. So we would need to make sure that we take 62 degrees and then turn that 37 minutes into degrees by making it 37/60ths. So that would be equal to 62.616 repeating degrees. And that's what we would want to put into our tangent then. So 7.5 times that tangent of the 62.616 repeating degrees would be equal to x. And then when we solve for x, then we get about 14.48 miles is how far away that fire would be then from that first ranger. And then in example 9 here, we have that the Golden Gate Bridge, it has two main towers of equal height that support two main cables. There's a visitor on a tour boat that's passing through the San Francisco Bay, and that visitor on the boat views the top of one of the towers and estimates the angle of elevation to the top of that tower to be 30 degrees. And after they sail closer, there's a detail that I forgot to put in here. As they sail 670 feet closer, then the visitor estimates the angle of elevation to the tower to be 50 degrees. So we want to approximate the height of the tower, right? So what's basically happening right here is we've got this tower from the Golden Gate Bridge that's very tall, right? And then down here below is where we've got the bay, so we've got all the water down here, right? So at one point in time, there's the boat over here, and it has an angle of elevation. So from horizontal, which is where the bay is, all the way up to the top of the tower, they measure an angle of 30 degrees, right? But then when they sail a little bit closer, so when the boat moves to a closer location, by a distance, so this distance right here is 670 feet closer, they now measure an angle of elevation here of 50 degrees. So with all of that then, we want to find h. So what is the height of the tower of that Golden Gate Bridge? Okay. So what's kind of key to recognize here is we do have two different right triangles existing in this. We do have this right triangle here that has a 50-degree angle and a right angle right here, where this side right here is h. But then this side down here, we don't really know what that is, so I'm just going to call it x, okay? And then we do have a right triangle that's a little bit longer that has the 30-degree angle in it. And it still has a height of h, that's the height of the tower, but now the base right there is going to be that distance of x plus the 670 feet that the boat moved closer. So this would be a distance of x plus 670, right? So within both of these triangles, when you reference either the 50-degree angle or the 30-degree angle, you'll have the opposite side be the height of the tower, and then the other sides that are labeled with x or x plus 670 are the adjacent sides. So opposite and adjacent could be used in a tangent ratio. So for the first triangle, if we tangent 50 degrees, it'd be the opposite over the adjacent. And then in the other one, the tangent of 30 degrees is equal to the opposite over adjacent, like this. Now, what we're trying to solve for, of course, is we're trying to solve for h. And so I could actually get h isolated and solve for in both of these triangles because I could say that in this first relationship that x times the tangent of 50 degrees is equal to h. And then in the other relationship, the quantity of x plus 670 times the tangent of 30 degrees would be equal to h. And so if I have that this expression right here is equal to h, and this expression right here is equal to h, then I could set those expressions equal to each other, and then be able to solve for x. So I could set x times the tangent of 50 degrees equal to x times the tangent of 30 degrees plus 670 times the tangent of 30 degrees. So on the right-hand side there, I did the distributive property where the x and the 670 had distributed, right? So since I do have x in a couple of different locations and they're on different sides of the equation, I'll want to get them on the same side of the equation at least first of all, which means x tan 50 minus x tan 30 would be equal to 670 times tan 30. And then because we still do have x in a couple of different locations, I could do some factoring by taking out the GCF that is x. And then x times tan 50 minus tan 30 on the side would be equal to 670 times tan 30. And then I can solve for and get the x alone if I divide it by the difference of tan 50 and tan 30. So x would be equal to 670 tan 30, and that's going to be all over the difference of tan 50 minus tan 30. And then you'll want to put that in a calculator. Make sure in a calculator you put parentheses around that difference. So you divide by that whole difference there. And that gives us then the value of x to be about 629.59 feet. Okay, now that doesn't solve for h at all for us because we're trying to solve for the height of the Golden Gate Bridge, but now knowing x will allow us to find what h is. So what we could do with this known x value now is we could substitute it into maybe like this triangle, and then use some trig to find h there. So since now in that triangle we know this is 629.59 and this is h and this is a 50-degree angle in a right triangle, we could still use the tangent ratio and know that tangent of 50 degrees is h over 629.59 and then multiply both sides by 629.59. So that's just going to multiply with the tangent of 50, of course. So it gives you that h is about 750.32, almost exactly. And so that right there would be the height of the Golden Gate Bridge then rising from the San Francisco Bay. Then example 10 here, we have that a window washer is on a ladder and they're looking at a nearby building that is 100 feet away from them. And the window washer notes that the angle of elevation to the top of the building is 18.7 degrees, and the angle of depression to the bottom of the building is 6.5 degrees. We want to know how tall that nearby building is, right? So think about where this window washer is, right? They're currently on a ladder, so they're up in the sky, which means that they're able to actually have an angle of depression. They can actually look down upon the bottom of the building, but they're not quite high enough to be above the top of the other building, right? So they have an angle of elevation to the top of that other building, right? So currently you have some building, right? And then on the ladder is this window washer, right? But there's some other nearby building that's a little bit taller, right? But we know that it's a distance of 100 feet away. And this person is able to have an angle of depression. So from horizontal, able to look down at the bottom of the building, and that's a 6.5 degree angle. But then they're also able to look up towards the top of the building at an angle of elevation of 18.7 degrees. Okay. So what you should recognize is that this horizontal is actually the same thing as the 100 feet distance between the buildings, right? And we want to try to find the height of the other building, which is this height right here. But what you could do is you could actually find what is this distance right here, x, and then also separately find what this distance is here, y, and add those distances together, and that'd be the overall height of the building. Because really, you can just take this right triangle right here, which has this leg length of 100, and find the other leg length of it, x, given that this acute angle here is 18.7 degrees. So x is the opposite and 100 is the adjacent, referencing the 18.7 degree angle. So the tangent would be opposite over adjacent of the 18.7 degree angle would be equal to x over 100, and then multiply by 100 to both sides to get x alone. So 100 tangent 18.7 gives that x is about 33.85 feet then. And then with the other right triangle that we have, where this is a 6.5 degree angle, and knowing this is y and this is 100, it's the same tangent ratio because y would be the opposite and 100 would be the adjacent to the 6.5 degree angle. So tangent of 6.5 degrees equals y over 100, and then multiplying by 100 to both sides gives you that y would be about 11.39 feet. And then with those two distances of x and y, you can just add them together to get the total building height. So 11.39 plus 33.85 gives you a total distance or a total height of about 45.24 feet then for the total height of that other building. Okay. And then this last example here, we have a vertical antenna that is mounted atop of a 50-foot pole. From a point that is on the ground 75 feet from the base of the pole, the antenna subtends an angle of 10.5 degrees. And we want to be able to find the length of the antenna, right? So we have a 50-foot pole here. And then there's a vertical antenna. Vertical means up and down. That's atop the 50-foot pole, right? So there's another extension to that 50 feet right there. But we don't know how tall the antenna is, right? So it says from a point on the ground that's 75 feet from the base of the pole. So if we go over this far, 75 feet, the antenna is subtending an angle of 10.5 degrees. So what that means is from this point on the ground, if we were to look up towards the top of the pole at some angle of elevation there, right? And then we were to look up towards the top of the antenna at some higher angle of elevation, okay? The subtending angle is only the angle that is how much angle we would need to increase from looking up to this point right here to this point right here. So it's only this angle, that's the amount of angle change to look up to the top of the antenna from the top of the pole, that is the subtending angle, okay? So that's all that we have to know, and we want to try to find the length of the antenna, right? So what might be helpful for us is to actually find what this yellow angle theta is, and we can do so because this triangle right here, formed by just the pole and the ground, is a right triangle, and we know two of the side lengths are 50 and 75, which is the opposite to theta and the adjacent to theta. So using a tangent ratio then, the tangent of that yellow theta would be 50 over 75, and then doing an inverse tangent of 50 over 75 would spit out what that acute angle has to be for us then. So we get then that 33.69 degrees is what that yellow theta angle measure is going to be. And then with that, if we were to mix together and combine both of those angles together, we would get an overall right triangle that goes to the top of the antenna. And that would have a 33.69 plus 10.5, a 44.19 degree angle. And then this is still going to be 75 feet. And then we could actually find what this overall length is with the combined antenna and pole if I called this x. And use again another tangent ratio because x is opposite and 70, this is 75 feet, not degrees, and 75 is the adjacent. So tangent of 44.19 degrees would equal x over 75. And then multiplying 75 to both sides, 75 tangent of 44.19 will tell you that you have about 72.91 is about the length of x. And then you just need to subtract away the 50-foot pole, telling you that then 22.91 feet is going to be the length of just that antenna then.